All right, well, so in this video, what we're going to be doing is some computation with complex numbers. This is part 2 of my complex numbers series. So computation, we can add and subtract complex numbers. So that's where we're going to start. And so if you have a complex number, a plus bi, a and b, c and d, all of these are real numbers. Remember that abbreviation for real numbers. So we have a plus bi plus c plus di. What we're going to do is we're going to add the real parts together, and then we're going to add the coefficients of the complex parts. So it's kind of like adding like terms, really. That's what it comes down to. Likewise, if you subtract, if you have a plus bi minus c plus di, we're going to subtract, because we're distributing that negative sign to the c plus di. So you're going to have a minus c, that'll be the real part of the complex number, and then b minus di. So let's do an example. So example 1, 5 plus 3i plus 4 minus 8i. We're going to add the real parts together, and then we're going to add the coefficients, which it's 3, and then this coefficient is negative 8, so we end up really subtracting. But you're going to have, the real part is going to be the 5, these two real parts added together, which is 9, and then the complex part is, you're going to have 3 minus 8, so it's going to be negative 5i. All right, so then for example 2, why don't you try it, see if you can get it right, and I will do it here in a second. All right, so we have 7 minus 4. You're going to subtract that part, and then plus I have negative 6 minus 2i. So 7 minus 4 is 3, and then I have plus negative 8i. I don't need to have the double sign there. I can just write 3 minus 8i. All right. So now multiplying complex numbers, you need to recall that I squared, remember I is the square root of negative 1. So if you square that, you end up with I squared equals negative 1. So it's just like FOILing. You're going to multiply a times c, and then you're going to multiply a times di. Then the inside, we're going to multiply b times ci, and I'm putting the I at the end. Remember, we can use the commutative property with multiplication, so you can do that. And then plus b times di. Okay, that's the general form, how we do this. Let's do example 3 with actual numbers in there. So we have 4 times 8, which is 32. And then I have plus 4 times 3 is 12i. And then I have minus 16i. And then the last two is negative 6i squared. So now remember what I squared is. I squared is negative 1. So that's going to become, we're going to replace I squared with negative 1, and I'm going to combine these two like terms, the complex parts. So I have 32, and then I have 12 minus 16i, which is minus 4i, and then I have minus 6 times negative 1. I'm replacing this I squared with a negative 1. So that becomes 32 minus 4i, and then that becomes plus 6. So now I can add the 32 and the 6. I get 38 minus 4i. Pause the video, do example 4, and then come back and check it. All right, so for example 4, you should have gotten 23 minus 41i. If you didn't, bring the questions you have to class, and we'll go over it. Okay, so then the next part, so far we've added, subtracted, and multiplied. Now we're going to do, we're going to use something called complex conjugates to do division. So a plus bi and a minus bi are called complex conjugates. So you just take the opposite sign of the imaginary part from the other term. So if you do that and you multiply a complex number times its complex conjugate, look what happens. Let's FOIL this. You have a times a is a squared, and then I have minus a b I, and then I have plus a b I, and then I have minus b squared I squared. These two cancel each other out, so I have a squared because they add to 0. Then I have minus b squared, and remember I squared is -1. So what we end up with is a squared plus b squared. And we have, when you multiply a complex number times its complex conjugate, what happens is the imaginary part disappears because they add to 0 here, and then we have this I squared is -1. So the imaginary part is no longer present. All right, so here's if you want to multiply example 5 by its complex conjugate, we would multiply by 5 minus 4i. Foil that and then get the result and see if you can get the same thing I'm getting. So 25 minus 20i plus 20i minus 16i squared. These two cancel out, so I'm left with 25. And then this is a -1, so it turns into plus 16. And what is that? We have 41. All right. So let's apply this to something. We're going to use a complex conjugate to write a complex number in standard form. Standard form is this a plus bi. So we don't want to have the complex part in the denominator. So what we're going to do is we're going to take this complex number in example 6, and we're going to multiply the top and bottom, because if I do the same thing with the top and the bottom, I'm really multiplying by 1, and I'll get rid of the I part in the denominator. It's kind of like rationalizing the denominator. When you have square roots, we try to get rid of the square roots in the denominator. Same kind of thing. All right, so I want you guys to do these problems on your own and then come back and check. I'm not going to do, well, I might do the answers to all of them, but I'm not going to go through all of them. You guys pause the video, do number 6, come back and check it. All right, so I'm going to go on the top, I'm going to go 2 times 3, which is 6. So I'm just doing the distributive property, and then 2 times I, which is plus 2i. In the denominator, 3 times 3 is 9. I have plus 3i. I have minus 3i. Those are going to cancel out. And then I have minus I squared. So the top is going to just stay 6 plus 2i. And in the denominator, I have 9 minus I squared, which means 9 plus 1. So I end up with 6 plus 2i over 10. Now I can factor out a 2 out of the top, and that would leave me with 3 plus I, and I can factor out a 2 out of the bottom. The 2's cancel out, so this in simplified form is 3 plus I over 5. Or you can write 3/5, that's the real part, plus the imaginary part is I over 5. All right, do examples 7, 8, do the rest of this page here, and then come check your answers after you're done. All right, so in example 7, you should get 26 over 29 plus 7i over 29. Example 8, 6/5 minus 3/5 I after simplifying. And then in example 9, 44 over 51 minus 6i over 51 is your final simplified version. If you got this, just recognize that they're both you can factor out a 3 out of the top and out of the bottom, and then it simplifies to what I have on the line there. Okay, so there's a couple of videos here. I'm going to post them on Canvas, and you should watch them. It shows you some examples of where this is applied in real life. And it's pretty interesting stuff. These fractals that this video right here is on fractals, which are a recent development in mathematics because it requires a computer to really graph a fractal, and this video shows you other places where fractals are used, which fractals involve complex numbers. And so fractals and iteration, we can do that in a different video. Right now I want you to go to this page in your notes, complex numbers and their real life application. So you guys can read through the where they're used in real life, and then we're going to go through an example of where they're used. Alternating current in electronics, electricity, require complex numbers to do the calculations. So an electrical current equation, V equals IZ. We're going to do a few problems with this. V is your voltage, I is your current, which is why we use J in electronics versus I, because I is already used for current, and Z is called the impedance. So you can rearrange this equation, and Z is equal to V divided by I. We can also separate the current and the voltage using complex notation. So if you're interested in that, you may want to read some more about that. Also watch the videos. Okay, so voltage is the difference in electrical charge between 2 points in circuit, and the units are in volts. The current is the flow of an electric charge, measured in amps. Impedance is the opposition of flow in alternating current. And in DC, the term resistance is used. So basically, it's like when we get our electricity in Seward here from Anchorage, so those transmission lines, it's a very high voltage and current in the transmission lines, but then it goes through a process where it's impeded, and then it's to a certain level that we can use in our homes. Okay, so let's do some problems. The impedance in one part of a circuit is 4 plus 2I ohms. So our equation, what was impedance here? The Z is your impedance. So I have V equals IZ. And our impedance is going to be replaced with 4 plus 12I. The impedance in another part of the circuit is 3 minus 7 ohms. What is the total impedance in the circuit? So we don't need to use this equation right now. What we're going to do to find the total impedance is we're going to add these two together. So I have 4 plus 12I ohms plus 3 minus 7I ohms. So you guys add those together and write down your result. And then go ahead and do number 2 on the next page, and 3, and come back. You can check your answers on those, and then there's more practice 4 through 9 through 10 on page 7 that I want you to go through and do all of those, and then do 11, 12, and 13. But I'm going to need to cover some more things for you to do 14 on. Okay, so go ahead and do that. Pause the video, go do those problems, and then I will do another video to show you how to do that last part. Okay, for the first problem here, you should have gotten 7 plus 5I, adding the like parts together. For problem number 2, the current, you should get 7 minus 6I after simplifying. And then number 3, to find the total voltage, you're going to multiply the current times the impedance, and the voltage is 20 minus 29I. Okay, so go ahead and finish up through, up through 13, and then you'll need to watch the next video to learn how to do the simplifying I to powers and the graphing as well.